So welcome back, everybody. I hope you're all enjoying working on your class projects and that you found the feedback that we gave on your projects useful. Feel free to send email to ask more questions about that. So today we're going to spend one lecture on something I normally give a 1.5 hour lecture on. So just in case you want more details, there's lots of hidden slides. And if you look at the recordings from last year, this whole thing was given with more details, spread out over 1.5 hours. So here's the big idea in solving the problems we're going to talk about today. So today's problem, as well as several others that we've already considered, have the property that the answer at each point depends on the data at all the other points in the problem. So today, what's a point? It may be a charged particle, which is exerting an electrostatic force on everybody else. And so every particle has to depend on all the other particles to get the right force. It also came up when we were solving elliptic partial differential equations, and we talked about multi-grid. It depended on all the data to find the value at any point. And in graph partitioning. So the answer depends on every edge and every vertex. So it seems that no matter what you do for these problems, if everybody depends on everybody, the work is going to be n squared, both measured in work and communication. So the trick to beat n squared is the following. So suppose that the stuff that's far away gets simpler. And I've used an example of that for gravity before, and I'll do that again later. But if the data that's far away from you somehow gets smoother or simpler and compressible, then we can go a lot faster. And so what we're going to do is use that idea, and the idea is, for example, the Andromeda galaxy has lots and lots of stars in it, but it's well approximatable by its center of mass. And conversely, the Milky Way looks like a dot if you're in the Andromeda galaxy. If we apply that idea recursively, then we're going to go from n squared to either n log n or order n for a whole bunch of different problems. And so today we're going to concentrate on things that look like gravity or electrostatics, but in fact it's been extended to any function that sort of gets simpler or smoother the farther away you are, and that's a lot of different applications. We did it in a previous lecture for multi-grid. In that case, we replaced a fine grid by a coarse grid recursively, and that's how we compressed the information that was far away. And for graph partitioning, we did the same thing. We threw away every other point recursively and replaced our fine graph with a coarse graph to get down from order n squared to order n log n. And now I'm going to say that any idea that's been used 3 times is a standard technique. So that's why it's a big idea. So I will guide you through some motivation, show you some examples of, remind you of the n-body problem and the different kinds of forces that we care about. Then I'll give you the high-level overview that I just did about how do we do this compression in a recursive way. And then there's going to be 2 algorithms that I'm going to talk about that have been designed for this, Barnes-Hut and fast multipole. They both share the same data structures called quad trees or in 2 dimensions or oct trees in 3 dimensions. And we've seen quad trees before. They came up when we talked about how to divide up dense matrices across multiple processors, but we'll see them again. And so that'll be the first few bullets there are basically doing the math, approximating the math for these algorithms, and then we'll talk about how to make them run in parallel and some of the big speedups that people have gotten. So just to remind you about what does a particle simulation look like, I have a bunch of particles numbered from 1 through n, and I'm going to have a bunch of time steps. I want to start at time t equals 0 and get to a final time. So at every time step, I'm going to compute the force on each particle, I going from 1 to n, and then I'm going to take a little time step and use that force to move the particle a little ways. And that's just using F equals ma in the usual way. And then I'll compute some interesting property of all the particles, and then I'll update the time step. So all the work is spent in computing the force in the particle. And just to remind you, there are 3 kinds of forces and 3 different ways of parallelizing them. There's what we call the external force, the easy stuff, the nearest neighbor force, that was homework 2, and then the n-body force, which is what we're going to talk about today. So the external force is the easy, embarrassingly parallel part. So if you're a fish in an ocean and you know where you are, all you have to do is know the current, where you are, and everybody can do that independently. Then there's the nearest neighbor force, where you have a cutoff distance. You don't depend on people who are far away. In physics, that could come up from van der Waals force, and we saw how to parallelize that in homework 2. And today we're going to concentrate on the n-body force, where everybody depends on everybody. So just a little notation. So the force on particle I is going to be the sum of all the other particles of the force on I due to k. And the two ones that I'll concentrate on today are just inverse square laws. So in 3 dimensions, what's the force? It's the vector that points from particle I to particle k divided by its length cubed times some constant, which depends on masses or charges, whatever, in 3 dimensions. And to make the math easier, I'm going to do it in 2 dimensions. In that case, it's an inverse, so the 3 in that exponent goes down to 2. And so it's an inverse first power law. And so that'll make it a little easier to do. So, and if I do the obvious way, it's going to be n squared, but we're going to do better. And just to remind you where this fits in the overall picture that we've used since the beginning of the semester, here are all the 13 motifs that we care about, that we can divide lots of computations into. And today we're going to do the n-body one, which comes up in HPC, but it also comes up in games, and it also comes up in, I hope, a surprising application that I'll show you in a few slides. So here's some applications, and the way I'm going to do this is I'm going to walk through consecutive Gordon Bell prizes. So these are prizes that were given at supercomputing for the biggest, coolest, fastest parallel implementation of something. And so let me go back to 1992, which is when one of these first algorithms were invented. And this was an application in celestial mechanics. So this was a huge supercomputer at the time, a whopping 512 processors, so not too big by today's standards. And what they did was they had 17 million particles, and they wanted to move them 600 time steps, which is 24 hours in simulated time. And they sustained, by using this algorithm I'm going to tell you about, a whopping 5.2 gigaflops, almost as fast as your laptop. And so, and it was for 44,000 flops per particle per time step. And they only got 1% accuracy. So this is going to be the trade-off. We're giving up n squared complexity, but we're going to have to do a little bit of trade-off in accuracy. This was the first time people did this. 1% was good enough for them. And so the real comparison to make is that if they had run the n squared algorithm, how long would this simulation have taken? It took them a day. The n squared algorithm would have taken 18 years. So a speed up of 6,000 or so. So that's why they won the Gordon Bell Prize. Let me move up to 2009. And this was a cluster of 256 NVIDIA GPUs, and it was almost exactly the same number of particles, about 17 million. And now they won a different kind of Gordon Bell Prize, because there's also a prize for the cheapest simulation, measured in dollars per gigaflop. And so in this case, the record that they set was they managed to run at 20 teraflops at full speed, and they did it for a cost of $8 per gigaflop, counting just the hardware. So let me give you, we're going to move up in time, but let me just give you a few other sample applications. So there's molecular dynamics, where you're trying to see how a protein folds or DNA folds, something like that, and that is again an electrostatic force. Another example is plasma simulation. You're trying to understand whether a tokamak works, or how a star is going to form. I have colleagues over in Quarry Hall who are interested in designing electron beam lithography devices so they can do manufacture smaller and smaller semiconductors. But the most interesting application that you might be surprised by is hair. So this is some work that was done by a former CS267 GSI, Michael Driscoll, who spent a summer at Pixar. And his job was to write the code that was simulating Princess Merida's hair. So in the movie, like Brave or the many other movies she's been in, if she waves her head around, then her hair bounces around in a very realistic way. And the way they do that simulation is that each thread of hair is represented by a bunch of charged particles that repel one another. And so when her hair moves around, the hair threads repel one another, and it looks kind of realistic when she moves it. And so every movie with her in it has been using that software ever since he was there. So you can appreciate the n-body problems for that. One other thing I should mention is that what he learned was that if you only spend 3 months working at a place like this, you don't get screen credit. So otherwise, you'd see his name every time you went to the movie theater. But that's all right. So here is going to be the intuition that we use for reducing the number of particles in the force sum. So all the divide and conquer algorithms we're going to be talking about use the same intuition. So to repeat something I said before, you walk out, you want to compute the force of gravity on the Earth due to everything in the universe. You walk out at night, you look up at the sky at all those little white dots, and you say, oh, that's a lot of terms in my sum. And then you realize one of those white dots is the Andromeda Galaxy with lots and lots of little white dots inside of it. But your intuition was fine. We're going to replace the Andromeda Galaxy by its center of mass and its total mass. And conversely, we'll do the same for the Milky Way if you're in the Andromeda Galaxy. So we need a criterion for deciding when you look like a little white dot. So here's the math to make that decision. So we're going to divide the entire domain into little boxes, and that box will fall out naturally from the data structure. In this case, it's a quad tree, so we're going to divide up into little boxes. And here is where we are, and I would like to compute the force on the Earth due to all the particles in that box. So I just need to know how big is the box. It is going to be a d by d box. I have to know how far away I am from its center of mass, and I'm going to take that ratio d divided by r. And if that's small enough, less than some threshold that's going to be the user gets to choose, depending on how much accuracy the user wants, that's going to be my criterion for deciding that this box is small enough to replace. What if it isn't? Well, I'll just divide it into 4 smaller boxes, you know, and run the same little algorithm there. D will get smaller, and eventually I'll be able to replace it. So this idea of replacing something big and complicated by its mass and center of mass is not new. Newton obviously approximated the Earth by its center of mass when the apple fell, but he didn't do it recursively, so that's why he didn't see this. So just to explain the recursive one, which is pretty simple. So here's the Earth, there's the Andromeda Galaxy. The Andromeda Galaxy is pretty complicated. The planet Vulcan is in there. And so suppose I want to compute the force on the planet Vulcan by some other distant solar system that's still inside the Andromeda Galaxy. Well, I'll use the same criterion. I'll take the box of now much smaller size, d1 by d1 around that solar system, and the distance from Vulcan to that solar system, and I'll again ask, is d1 divided by r1 small enough? And I'll just keep doing that over and over again at every level of the tree. So let me tell you what the basic data structures are. Now, I should also say that I have a bunch of hidden slides which have the code written on them, but I won't do that in today's lecture to fit it into our time. But it's all simple recursive code. And so what we need to do, let me just do it in 2D first because it'll be easier to draw, is to describe the data structure. So initially I start with a big black box in which all the particles live, and that's represented here by the root of the tree, which is the same color, black. Then I divide that into 4 subsquares which have dark blue boundaries corresponding to those 4 dark blue dots in the tree. Those are the children. The next level, I break each of those squares into 4 smaller squares that have red sides corresponding to the 4 red dots, and eventually I get down to the light blue dots. So this is what my data structure is going to look like, and I'm going to use this both to traverse the tree. I'm going to use this as the algorithm, and I'm also going to assign it geometrically to where the particles live. So that's the 2-dimensional version. And the 3-dimensional version is quite simpler. That's called an octree. And now each vertex in the tree has 8 children corresponding to the 8 octants, and I'll just draw one level here. So, and to keep the algebra simpler, I'm going to keep it all in 2D because that way I can just use one complex number to indicate where I am. So it'll make all the calculus that I have to refer to a little simpler. So all those trees that I showed you before were uniform, right? I went down to the same level at every time, but in the real world, or the real universe, particles are not uniformly distributed. They're clusters of them in different places. And so what I want to do is actually build an adaptive tree that has finer structure only where they're particles. And so this is what the data structure will look like more generally. And so again, I have one vertex where, representing the big black box where everybody lives. If I divide that up into 4 dark blue boxes of half the size, each one of them is populated, so I have 4 children. But now there's only one vertex in there, so I'm done. I don't have to take that one and divide it anymore, or that one. But this one has 3 red children who are populated, so that one has 3 children. And that one, these 2 are done, so they stop right there. This one continues to have 2 populated light blue boxes and then some more brown boxes at the bottom. And so the way to make a correspondence between this geometry and this picture is that I have to somehow number these, traverse these boxes in a way that corresponds to going from left to right. So in all these pictures, I'm going to use what's called a backwards C ordering. So I'm going to start at the northwest corner, then I'll move to the southeast corner, and then the northeast, and then the northwest. So that's how I go from left to right here. So that will be how the picture works. Now, in practice, I probably don't want to go all the way down to 1 particle per box. That would be a little bit inefficient. So instead, there's going to be a tuning parameter, which we'll use later to make the algorithms go faster. I'm going to decide to stop dividing this box up when I get to some magic number, capital Q, excuse me, lowercase q, of particles inside that box. And so in this case, Q is 1, but in general, I have more. So why do I do that? Because once I get down to a box which has Q particles in it, and I don't divide it anymore, I'm going to use the direct Q-squared algorithm at that level. And so why is that a good idea? Because if I'm running, for example, on a GPU, it's much faster to do a direct, 10 squared or even 100 squared algorithm than to try to divide it up anymore. So the choice of Q will depend on your hardware. And let's see, and all the code for building this is pretty straightforward. It's just sort of, accessing a tree recursively. It's on a hidden slide, so you can read that later if you like. So what's the cost of building this data structure? I have to take each particle and insert it into the data structure. And so it's easy to see that the way the code works is I say, please take a new particle and insert it at the root. And if the root has children, keep going down until you find an empty box to put the child in. So the cost of inserting each particle is basically the depth of the tree. How far down can it go? And so the cost of the algorithm is the maximum, is the cost of inserting 1 particle. I'm going to do that n times. And inserting 1 particle is the depth of the tree. So to understand the complexity, how deep could this tree possibly be? There's sort of 2 cases, the most optimistic and a pessimistic case. Let's suppose the particles are all uniformly distributed. And so every box has the equal number of particles. How far down do I have to go until there's just 1 particle per box? Well, at the first level, I'll have 4 boxes, and then I'll have 4 squared boxes and 4 cube boxes. So I have to go down log n levels in order to fill everything up. And so that is going to be the depth of the tree if the particles are uniformly distributed, so the cost will be n log n. Now, particles are not uniformly distributed. How do I get a bound on how far down I could go? Well, here is the intuition. Let's suppose that my particles are represented by single precision numbers. So that means they have 24 bits in their fraction. So let me come here. So how do I decide whether I'm going to be on the left or the right? I need to look at 1 bit in the fraction that tells me, is it a 0 or a 1? How do I know if I go up or down? I look at the y coordinate, and I again just look at 1 bit. So every time I decide whether to go left or right, up or down, I need 1 more bit in my x and y coordinates. So how many levels can I go down? It's how many bits do I have in my numbers? So a very coarse upper bound is just the number of bits that you use to represent the data, and that would be in this terrible worst case when the particles were at adjacent locations represented by floating point numbers. It still gives you a linear bound. It tells you that even in this pessimistic case, it's a reasonable algorithm. Okay, so that's the data structure. And so now let's move on to Barnes Hut, which was the first one that was invented. And so this appeared in '86, and there were many, many later papers. And their goal in this algorithm was just to get about 1% accuracy. So that was what they were hoping for. It's gotten much better since then. And so how do I measure accuracy? It's going to be something called the root mean square error. So I take the approximate force for every particle, subtract the true force. That's a vector. Take its length squared, divide by the true force. So this should be hopefully something between 0 and 1. Add them all up and take the average. And so our goal is to make that about 1%. So here is the high-level algorithm that we're going to use for that. So first, we build a quad tree, and I already showed you how to do that. I didn't show you the code, but it's already there. Then, what we need to do, the second step, is for each node in the quad tree, which means for each node in the tree or each square in that picture, I'm going to compute the total mass and the center of mass of all the particles in each square. Okay, so that's what I'm going to use to compute the force if you're far enough away from that particular square. And this is a very simple post-order traversal of a tree. So what do? I start at all the leaves of the tree at the smallest squares, and I simply straightforwardly compute the total mass and the sum. And if there's only one particle per square, that's totally easy. Now, once I've done all the leaves, I go to the parent. And the parent has 4 children. And how do I get the total mass of the parent? I just sum the masses of the children. How do I get the center of mass of the parent? I just take the appropriate weighted sum of the center of masses of its 4 children. And once I've done the parent, I can go to the parent's parent and do the same trick, right? Just keep summing, and it's all very simple. And the amount of work is just a constant amount of multiplies and adds per node in the tree. So the total cost is just the number of nodes in the tree, which we know is cheap. Okay, now the interesting part is what do I do once I have all that information? For each particle, I'm going to traverse that quad tree and use that trick to say, is your box far enough away? I can approximate you by your mass and center of mass. And so for each particle that I do, and I'll put the code in the next slide, I will traverse the tree once. Only a little piece of the tree. So this is where the core of the algorithm is. So let's look at the code. Or, well, let me describe the code, the algorithm, and then the code will be on the next slide. So as I said, for each node, I can approximate it by using its mass and center of mass. So I need this criterion for deciding, am I far enough away? And here's the picture I used before. So suppose this is a particle, and suppose this is a square in the subtree somewhere. Well, I know the size of that square because it's the data structure that I built. It's very simple. I know where I am, and I know how far away this box is, and its center of mass could be no closer than that. So I can compute a bound on the distance. How far am I from the center of mass? And I take that ratio, size of the box divided by the distance, and if it's small enough, then I'm done. I don't have to look any farther inside that box. I just do a little computation and add it. Otherwise, I have to divide that box into 4 pieces and look farther down the tree. Okay, so let me now write the code. It all fits on one slide. And so what I'm going to do is loop over all the particles. And for each particle, particle k, I'm going to compute the force on particle k by calling this recursive subroutine, tree force. And there are 2 arguments. It's the particle I care about, and the second argument says, please compute the force on particle k from all the particles inside that part of the tree. And the root means everybody. Everybody except myself, okay? So this is going to be the recursive call, and here it is. So I'm computing the force on particle k due to all the particles inside node n, square n in the quad tree. And so I'll start by 0, because I'm going to have to add up a bunch of things. Now, if the node contains exactly 1 particle, I'm done. I just use the obvious force law between two particles, inverse square law, and I just compute it. Otherwise, I have to decide, can I approximate you? And I do what I said before. I say, how far am I away from that box? That's R. How big is the box? And if I'm far away enough away from the box, d over r is less than theta, then I just compute f approximately using the total mass and center of mass of that box, and I'm done. Otherwise, it's too close, and I have to look inside. So I call this subroutine recursively on the 4 children of that node, and I ask the same question. And I just use this exactly same subroutine. This subroutine is calling itself recursively. And that has to stop, because eventually I'll get to the bottom of the tree, and there'll just be 1 particle in it, so it does have to end. So and I claim that, and the analysis is on the hidden slide, that basically every time I call the particle, I'm going to do a constant amount of work at each level of the tree. And the number of levels of the tree is log n, so I'm doing n log n work. Now, I don't want to do all the counting carefully, but that's basically it. Every particle just sort of goes down the tree and does a constant amount of work at each level. So that is Barnes Hut. Are there any questions before I go on and tweak it? It's more than a tweak. The next algorithm is very famous to make it be arbitrarily accurate, but still fast. Yes?
It seems like you could speed it up.
Let's see, microphone?
Oh, sorry.
Grace, we have a microphone? If it's a short question, I'll repeat it.
Okay. Sorry, you might have actually just said this, but it seems like you could speed it up by not actually iterating through all the particles and just saying the approximate force on all the particles in this box is Like,
Microphone.
Okay.
It seems like you could speed it up a little by not, instead of iterating through each particle separately, saying, okay, I can say that the force on all the particles in this box is approximately the same from this other box over here.
So this routine is written so that I can compute the force on any particle, whether or not it's part of my original data set that I built the quad tree out of. So I can, so I can apply it either to the ones that I already have or a brand new one.
Oh, okay, fair enough.
Yeah, that's why we want to use it this way.
I see.
Okay. So now let's go on to the fast multiple method. And so this was appeared in a paper in 1987, which won the ACM Doctoral Dissertation Prize and eventually got both its co-authors into 2 national academies each. So this has been a very impactful algorithm. So how does it differ from Barnes-Hut? So it's very similar in a lot of ways. So the first thing is that rather than computing the force at each point, I'm going to compute an expression for the potential. And then I'll remind you of the physics in the next slide. Once I have a formula for the potential, all I have to do is differentiate it and I can get the force. So it's going to compute potentials instead of forces. Then it's going to, in order to be more accurate, because this one you can run and get 16 digits if you like, you can decide how much, it's going to use more information in the box than just the center of mass and the total mass. And you get to decide what you want. It turns out it basically does a Taylor expansion. And you get to decide how many terms in the Taylor expansion you want to keep. And each extra term basically gives you one more bit of accuracy. So if you want lots and lots of bits, well, you know how many terms you have to take. So it's a very simple error analysis, which I won't say much more about. It turns out that Barnes-Hut is just the first 2 terms of the Taylor expansion. So it just sort of looked a little farther in the same direction. That's all. So that's the easiest way to describe the math. That's in 2 dimensions. In 3 dimensions, it's more complicated. So in compensation, we don't have to do this trick anymore of saying how big is the box and how far away I am. There's a very simple, all you have to do is look at who your cousins are in the tree. And that tells you if you're far enough away. So it's going to be a much simpler derivation of when you're far enough away. Yes, and so I'm going to use a fixed number of boxes. So the idea about Barnes-Hut is if you wanted more accuracy, you increase the number of boxes. And in what fast multiple is, it's going to use a fixed number of boxes, but if you want more accuracy, you need to take more terms of the Taylor expansion. So that's going to be the way it works. There are actually going to be 2 kinds of expansions that I need to tell you about. One of them is analogous to Barnes-Hut. I'm going to call that an outer expansion. That tells you if I'm far away from a box, what's the force on me due to everybody in the box? So that's the analog of mass and center of mass. But what I really want is the output of this algorithm is a formula for the potential inside a box due to everybody outside. Then that's what I need to evaluate to say what is the force on me. I need to know that or differentiate it. So what I'm going to do is remind you quickly of the physics of potentials and forces and what they have to do with one another, and then just do the very, very simple 2-dimensional case where I can do it all with just one complex number, so with x and y coordinates. So what I'm going to do, as I said, the fast multiple method is going to compute an expression for the potential, which you can evaluate or differentiate at any point. So just to remind you, what's the potential, gravitational potential in 3D? It's an inverse 1 over r law, 1 over the distance. So there's the distance between a particle at x, y, z in the origin. And if I know the potential, how do I get the force? I just compute its gradient. I differentiate it, the potential with respect to x, y, and z, and I get the usual expression, the vector pointing from the particle to the origin divided by its length cubed. So what the fast multiple method is going to do is going to give you an expression like this to differentiate, and then you can get the force. Now, rather than 3D, I want to keep it simpler. I'm going to do it in 2D. In that case, the potential isn't 1 over r anymore, it's log r. And when I differentiate that, I get a vector divided by r squared instead of r cubed. So that's the 2-dimensional potential. And it turns out that's going to make my algebra simpler because in 2 dimensions, I'm going to use not 2 numbers as coordinates, I'm going to use one complex number. Because if I know the x and y coordinates, I'll just say that's one complex number, x plus the square root of minus 1 times y. And so all of my algebra will just be in terms of one complex number, z. Now, what's the potential? It's still log of r. What's r? It's the absolute value of that complex number. And that's just the real part of the log. And this is going to make my algebra even simpler, because if you remember polar coordinates, z can be written as its length times e to the I theta. When I take its log, I get log r plus I theta. And so I'm just going to say log of r, log of z, and then I can just drop the word real from all of my computations. So it'll just make the writing down the algebra much, much simpler. So I just need to compute the log of a complex number. And then the force is, the complex number divided by its length squared. Now, this is all for gravity and electrostatics, but a few years ago, people realized that this trick works for any potential. It doesn't have to be inverse square. All this code and this infrastructure will work for any force that gets simpler the farther away you are. Or smoother, or somehow simpler, right? And that's an awful lot of different kinds of code. And it turns out you can write this so that all you need is a black box that takes as input 2 particles and it returns the potential between them. And the software will generate all the other approximations for you automatically. But I'm just going to do the inverse square law in order to explain how it works. Okay, so here's the potential at a point z due to all these particles. So n different particles, and they're located at these complex numbers, z1, z2, z3. And so as I said in the previous slide, what do? I sum over all the particles and take the mass times the logarithm of the distance. And then the log of that is just, as I said, put the real, just take the real part of the log of a complex number and using polar coordinates, and I'm just going to drop the word real from now on. So this is the expression that I need to expand. Now, when do I want to approximate this? It's all the particles are in a little box. Z1 through Zk are all in a little box near the origin, and capital Z is far away, much, much bigger. And so that means Z is much bigger in absolute value than Zk, so let me factor that out. So I'm going to replace Z minus Zk by Z times 1 minus Zk over Z. And the log of the product is just the sum of the logs. So I get a log z term, and then I get the log of 1 minus a tiny number. That's what I'm going to take a Taylor expansion of, right? Because 1 minus a tiny number, take a log, it's easy to approximate. Okay, so now I have this sum here doesn't depend on k anymore. So let me sum that separately. I get the sum of the masses times log z, so that's the total mass times log z. And then I get this term here, which I'm going to do a Taylor expansion of. So who remembers from freshman calculus, what's the Taylor expansion of 1 minus a tiny number? That's not very hard. It's just the number to the exponent e divided by e. So it's this to the first power divided by 1, this squared divided by 2, this cubed divided by 3. That's that Taylor expansion of this expression. And so there's the sum. And I'm only going to keep a finite number of terms there. So let me swap the order of summation. So I'm going to sum e on the outside. And so here is the z to the minus 1, z to the minus 2, z to the minus 3. And this is the coefficient of the Taylor expansion. Right? So I'm going to call that alpha sub e. So alpha sub e is the sum over all the particles of the mass times its location to the eth power over e. That happens to be called a multipole expansion, which is where the name of the algorithm comes from, the fast multipole expansion. So I haven't made any approximations yet. This is all exact. Now, here's the approximation. I'm just going to chop off this Taylor expansion. I'm just going to keep the leading r terms. And it says that if I throw away the leading r terms, all the other terms are going to be at least this small, the max of zk over z divided by, to the r plus 1 power. And so that's going to decrease, and geometrically, and so I can pick r, as big as I like. So if you notice, what are the first 2 terms of the Taylor expansion? Well, there's a total mass, and then there's just this weighted sum. So this is exactly the same information that Barnes-Hutt used. And so I'm just taking a few more terms that, beyond what Barnes-Hutt would have used. Okay. So that's all the math that I need to keep going. I'm just going to keep the first r coefficients here. So I need to remember m, and I need to remember alpha 1, alpha 2, ... alpha r to keep that. And I'm going to call that an outer expansion. So that's going to be the generalization of Barnes-Hutt, just remembering the mass and center of mass. And of course, I don't want to just do that around the origin. I want to do that expansion around any box. whose center is maybe z sub n, that's the center of this box here. And so here's what the expansion looks like if I'm expanding around not the origin, but around z sub n. So I just shift everything by z sub n. And so what data structure do I need there? I just need to remember the total mass and all of these Taylor coefficients, and then I need to remember where the center is. So that's the data structure that I'm going to use that replaces the one in Barnes-Hutt, which was just the first two terms, mass and center of mass. And so the question is, how many terms do I need to take? And if you do the algebra, it turns out that if I only plan to evaluate this formula when I'm not in a nearest neighbor, so this is a d by d box, so as long as I'm a little bit farther away, I'm outside here, the error is going to be 1 over 2 to the r, where r is the number of terms that I pick. And so if I want 24 bits of accuracy, I know I don't need more than 24 terms. So that would be enough for single precision. And that's very pessimistic. You probably need many, many fewer. But it tells you that the error goes down quite rapidly as you increase the number of terms. Okay, so this is the data structure that I need, and it's going to be used to evaluate the force outside this bigger box, this 3D by 3D box, due to all the particles inside this d by d box on the inside. Okay, and I'm going to build that in a, by traversing the tree just like I did in Barnes-Hutt, going from the leaves, going up to the root. So, but what I really want, the output of the algorithm, is what I want there is a formula, so that was called outer. Now what I really want is inner. I want a formula for the potential inside this box due to everybody outside. That's the final outcome of the algorithm. I want to, for every box, for every particle, I know what box I'm in, and I want to evaluate the potential due to everybody. And that's called an inner expansion. So I want a formula that says what's the potential inside here at a point z, at a box centered at zn, due to everybody outside this bigger box. That is going to be represented by a polynomial, right? Because that only has to be true inside a small area. So there I have a polynomial centered at zn, and it only has to be accurate inside that little box. And so my ultimate output of the algorithm is going to be this formula inner for every little box. Okay, so I need to have both of these data structures are going to be living in my algorithm. Okay. So now, and as they're backup slides with more details on the algebra, but I'm just doing a high-level description here. So here is the whole algorithm on one page on what I'm going to do. I begin by building the quad tree. That's identical to what I did in Barnes-Hutt. Then, very similarly to Barnes-Hutt, I need to build the outer expansion for every node in the tree. And I do it the same way I did with Barnes-Hutt. I start with all the leaves, and I do, which have one particle in them, say. So I compute the outer expansions there. Then I move up to the parent, and I combine the 4 children, and I say, okay, what's the Taylor expansion just by sort of summing the Taylor expansions of my children, and I get the Taylor expansion for the parent. And I move my way up the tree. The algebra is a little more complicated because I have to, the Taylor expansion is centered, at one point in the child, and I have to move it to the center of the parent, but it's just basically, some algebra that goes back to freshman calculus. Okay, so that's that step of the tree. And that's traversing the tree from the leaves going up to the root. So that's called a post-order traversal. The next step is I need to build all those inner expansions. So in that case, I start at the top of the tree, and I work my way down to the bottom, and I say I want a formula that gives me all the expansions for all of the force, the potential inside each box due to everybody that's far enough away. And so that's going to be some new code that I'll have to show you. Now, going back to this picture here, I now have a formula for the force inside every box due to everybody who's far enough away, one box away. What about the particles that are my nearest neighbors that are right here? For those, I'm just going to use the direct algorithm. So I'm not going to try to approximate them. There are not too many there. I'll just use the exact formula, inverse square law or whatever it is, if you're close enough. And that's going to be a sort of a constant amount of work, because at that point it's not very big. Okay, so now let me talk about how to do build outer. And I said this was a traversal where I just have to do the children and then do the parent, and then combine them to do the parent. And to remind you, in Barnes-Hutt, all I had to do was add the masses of my children. I got my mass. And all I had to do was sort of take the weighted sum of these guys' center of masses to get the center of mass of the whole thing. Now I have to add these expansions, and it's a little more complicated, but not too much. So here's what the function looks like. I'm going to do build outer, and I'm going to call it on the root. And if I'm a leaf, then I only have one particle, and I use that formula that I had before. That's very easy. And so I get this sum, which has all the coefficients, the center of the box, and m. And then I have to work up to the parent. So what I do is a recursive call. So if I don't have if I'm not a leaf, I'm a parent, then what I do is for all my children, I go build their outer expansions. So here I will call this subroutine recursively on my 4 children, so I'll get all their expansions, and now I have to combine them. So how do I combine them? What I have to do is 2 things. Well, I have to take that expansion, which is centered at 4 different points, and shift it so that it's centered there. So this is sort of freshman calculus. I have a Taylor expansion around this point, and I want to recenter it to be around a different point. And that's just taking a bunch of linear combinations of the Taylor coefficients to move it over. And I've hidden all of that algebra in this subroutine outer shift. So it just takes an expansion around that point, C sub k, and it shifts it so it's around the common center of the whole box. I do that for each child. I'm looping over all the children, and I just add up the coefficients. Okay. And so what's the cost? I'm basically doing a constant amount of work at each node in the tree, and so the work is proportional to the number of nodes in the tree, and that's order n. It's the same, the number of particles, and that's the same as for Barnes-Hut. Okay? And if you want to see the algebra for how this works, it's all on hidden slides. Any questions? So this is totally analogous to Barnes-Hut. So this is what's new. And this is going to be different. We're no longer going to be asking, do you look like a little white dot? We're going to have a simpler kind of combinatorial way to say that. So now I'm going to traverse the quad tree from the top to the bottom and convert the outer expansions to inner expansions. Okay, so suppose that I've gotten down to this point. There's a parent node, it's that red node, and I have an expression for the force on all the particles inside P due to all the particles that are not in nearest neighbors. So I've colored it red. So I have an expression from the parent for the force or potential inside that box due to everybody who's at least 1 box away. So now I want to do the 4 children. So node n there is a child of that parent. Okay, so I need a formula for the force inside n due to everybody who's not a nearest neighbor. So everybody who's not one of those nearest neighbor boxes. So how do I get that? Well, for my parent, I know all the red ones. That gives me all those that are far enough away. But I now need to look at all of my cousins in the tree. These are just your first cousins in the tree. So these are all nodes that were not counted by your parent. They're the same size as you are, but they're at least 1 away. And I've labeled them all by I. Those are called the interaction set. So for each one of those, I need to sort of take into account their force on me. So for each one of these, I need to say, give me a formula for the force inside n due to the particles in I. How many of these guys are there? Well, it looks like there are a lot of them, but it's pretty easy to figure out. This is a 6x6 box, so there's 36, and then my nearest neighbor is in me, that's 9, so it's 36 minus 9. There's 27 of these things that I have to sum. And in 3D, you can imagine it's a little bit more. Okay, so what we're going to do in order to make this work is I need 2 subroutines, again, which just do a bunch of algebra, and I'm going to summarize them here. So I have a formula for my parent, which says what's the force inside here due to everybody who's far enough away, and that's a polynomial, and the polynomial is expanded around the center of the parent. And so what I need to do is change that so that instead of being centered around the parent, it's centered around the child. Children are always very centered on themselves, so it's not surprising we need a subroutine like that. So here it's called inner shift. It takes a polynomial centered at the parent, and it recenters it around the child. Okay, so there's a subroutine that just does a bunch of algebra. And then I have to do another one, which I'm calling convert outer to inner. So I'm going to take the outer expansion of each one of these guys. So remember, what's an outer expansion? It says, what's the force if you're far enough away, if you're not nearest neighbors? N is not a nearest neighbor. So I'm going to take that outer expansion of all the particles inside there and convert it to an inner expansion around N. So that it's only valid inside N. Again, just a bunch of algebra converting one Taylor expansion to another. So these are just going to be subroutine calls, inner shift and convert outer to inner on the next slide. So all the code fits in a few lines. It's again just recursive. So I'm going to do build inner, and I'm going to do that at the root. And it's going to eventually call itself recursively and build the inner expansion for every node in the tree. So, so the output is going to be the list of all the polynomial coefficients in the center. So the first thing I say is, who's my parent? Because I have to go up and get the parent. If I'm the root of the tree, then the parent is nil. There's no work to do, right? Because there's nobody there. And then, as I said, I take the inner expansion of the parent. So that's everybody in the red zones. And I shift that to be at the center, and I call inner shift. So that's the first thing that I do. Then what I do is I loop over all of these blue boxes, all the points in the interaction set. So for all I in the interaction set, I get their outer expansion, and I convert outer to inner and center it around me, the child. And I just add them all up, component by component. And then once I build mine, I do the same thing for my children. I build inner for all the children. So now I'm the parent of my children, and I have to pass my information to them. So this is the recursive subroutine. And the cost is very easy to analyze. I'm doing a constant amount of work, albeit pretty large, at every node in the tree. So the cost is just proportional to the number of nodes in the tree, which is n. So there's the algorithm that I need to run and parallelize. And so that's the lion's share of the work. There it was. And then finally, I have to do my nearest neighbors, those boxes that were right next to me, because I'm not going to divide them anymore, and I just use the direct order n squared law, because there's not enough particles in them to worry about. Okay, so that's all the math. And now we're going to move on to the parallelization. Are there any questions about the math? Okay, as I said, there are lots of backup slides and lectures, longer lectures recorded from a couple years ago. So now let's move on to parallelization. It turns out there's a common way to parallelize both these algorithms because they share a lot of structure, obviously. And so here's the four-step approach to parallelizing it. We're going to build a quad tree, and that's going to require some interesting load balancing issues to get it all to be, the work spread out evenly among all the processors. Then we have to traverse the quad tree from the leaves to the root to build the outer expansions. That was just mass and center of mass for Barnes Hut, and a little bit more complicated for fast multipole. Then, just for fast multipole, we have to do that traversal from the root to the leaves and build all the inner expansions. And then finally, for every particle, we have to traverse the tree and compute the force, or the potential. Okay, and so that will be more easy to parallelize. So it turns out that given that common structure, there's sort of one scheme that works for all of these. I mean, you have to tweak it a little bit for the different algorithms. And this was actually analyzed in a PhD thesis here a while ago, where the student, David Blackston, built an auto-tuner that sort of did some tuning over all the different parameters we're going to describe to try to figure out what's the best way to divide it all up, on your particular architecture. So we have to assign regions of space to each processor, so we have to do some load balancing. And since particles are not uniformly distributed, there's some cleverness that's required there. And so we have to be careful so that not only is there equal work assigned to each processor, but there's a lot of locality, right? For all the usual reasons, we don't want to have to go to other processors all the time to get nearest neighbors. We would like all of the geometrically nearby particles to be assigned to the same processor, if at all possible. Okay? And we're going to use an idea called space filling curves that we used before for dense matrices to try to do that. Then, each particle is not only going to store, so what does each processor going to store? So remember, for each particle, what I need to do is start at the root of the tree, traverse it down until I get to a leaf in order to compute the force. So it would be silly if there were only one copy of the root of the tree, because everybody needs to look at that. Because every particle for whom I want a force needs to start at the top of the tree and traverse down. And fact, the next level of the tree, you know, the children of the root are probably all going to be traversed by everybody too. So what I'm going to do is replicate part of the tree on every processor. So everybody is going to get a copy of the root, because everybody starts there. They're probably all going to get a copy of the children, and then I need some rules about which subsets of that whole tree to replicate in each processor. And once I do that, it's going to be no communication at all is going to be required when I actually evaluate a force, because everybody will have their unique subset of the tree that they need to evaluate forces locally. Right, so I need to do that, and the name of this nice subset of the tree that everybody gets is called the locally essential tree. That's what you need to evaluate the forces on the particles that are in the geometric region that you've been assigned. So I'm going to replicate some data, that's not going to be very much, and I'll get embarrassing parallelism as a payoff. Okay, so that's going to be the plan. So here was how they, this 1992 Gordon Bell Prize decided to try to divide up the work. And this actually works pretty well in 2 dimensions, but not so much in 3 dimensions. So it's still going to use a quad tree, but now it doesn't have to be an evenly shaped quad tree anymore. So the first step, I'm going to divide the quad tree, all the particles into the left half and the right half, and I'm going to choose where this blue line sits so that half the particles are on the left and half the particles are on the right. Then I'll do the same thing recursively. I'll take this half of the particles and I'll choose a red line and I'll move it up and down until half the particles are below and half the particles are above. Same thing on this side, but there's no reason these 2 red lines should line up, because, you know, I could have more particles up there and down there. Again, so that's a horizontal division. Then I go back to vertical, and I choose the blue lines, and I move them left or right, so half is on the right, half is on the left, and then the brown lines. So every one of these rectangles contains an equal number of points, and it can follow the density. And so if I have 16 processors, each one will be assigned one of those rectangles. And for 3D, it's a little more complicated. This would be a plane, and then I would choose more planes, and that doesn't work so well, and there's a better idea. But this is okay for 2 dimensions. And so what I want to do now is have a data structure which has been reinvented a couple of times. It's called both cost zones and a hashed octree. We'll use the name cost zones. And so what I need to do is have some way of aligning this quad tree with this geometric structure. And what I'd like to do is have a way so that adjacent nodes, leaves in this tree correspond to likely geometrically adjacent regions in space, so I can minimize communication. And so the idea is I build a quad tree, and then for each particle, for each leaf, I have some sort of measure of how much work it takes, which could be just the number of particles inside or something more complicated. And then I start just going from left to right until I have, in case if I have 4 processors, a quarter of the work. And I'll say, okay, the pink processor gets the first quarter of the work. Then I start counting again until I get to the next quarter of the work, and I assign that to the green processor, and then the brown processor, and then the pink processor, orange processor. So the question is, how do I choose the ordering from left to right so it corresponds to contiguous regions in space? And I'm going to use this idea called a space filling curve. So I'm going to have a way of traversing all of these littlest squares, which correspond to the leaves, that in some sense makes them contiguous. And there are a lot of ways to do it. And this one is going to be what's called the backwards C order. So recursively, I'm going to do all those squares in the southwest, then I'll do all those squares in the southeast, then the northeast, and then the northwest. So these come first. How do I do these? I'll do the same thing. I'll break it up and do first the southwest subcorner, then the southeast, then the northeast, and then the northwest. So I'll do it that way. And then finally, inside each of those, I'll break it up again into a backward C and do the same thing. So, in other words, these first 4 nodes correspond to those 4. The next 4 correspond to those. The next 4 correspond to those. The next 4 correspond to those. Then I start over here and I grab the next 3. And I take all those pink ones, that's the load balance work, and I assign that to the pink processor. Then I continue with the green and I grab that one, then those 4, then those 4, then those 4, then those 4 and those 4, and those go to the green processor. Then I get the brown ones, and then I get the orange ones. Okay, so that's the backwards C ordering, and there's other orderings you could imagine too. Okay. So, and this works quite well in 3 dimensions, even though I've only drawn it in 2 dimensions. And there's a simple sort of hash function where you can sort of assign each of these, a location, an index, and interpret each consecutive bit as to where you are in the tree. Okay, so the way I've described this, let me go back here, is I built the tree, and then I looked at it and figured out how to assign work to processors. But the whole reason for doing that was to make it cheaper to build the tree in the first place. So I sort of have a chicken and egg problem. It's not practical to build the tree in order to compute the cost zones to figure out how to build the tree. I don't want to, repeat that. So what's the idea to get around that? I'm just going to do random sampling. I'm going to take a random subset of all the particles, build the tree for them, and then use that as my best guess to build the global tree. So all the processors will take their particles and send a small random sample to processor 1. Processor 1 will build this data structure and, and decide, roughly, how many particles belong in each region. And then it's going to broadcast that tree to all the other particles, and they will say, oh, now I know where to send my particles to, and the tree is sort of built immediately. And so that is the best way to do it. And you may, obviously, as the particles move around, because we're doing a simulation, they're moving, you may need to update it occasionally. But as long as, that's one reason to keep this quite cheap, because we don't want to have to, if we're updating it frequently, this would be expensive. But you can obviously let it get a little bit unbalanced before you repeat this process. Okay, so the next question is, how do I decide which subset of that tree should be replicated in every processor? And so that I don't have to talk to anybody, once I get another particle in order to compute the force on it. And there have been 2 approaches that have been proposed. One was started with shared memory, and the other one was worked on distributed memory. So the shared memory one, the motivation was, well, isn't the cache supposed to figure this out for me anyway? Suppose I have a machine with a bunch of multi-core nodes. Each one of them has its own local cache. It's just going to go to main memory. It'll touch it. If it touches it, comes into the cache, and it stays there, and it's all done. That worked for a little while, but it stopped scaling. And the amount of local memory just kept growing. The cache was, if you like, a little pessimistic. It just grabbed too much data, and so it doesn't scale up to large numbers of processors. So that was called a receiver-driven protocol. The receiver just grabbed what it thought it needed, but it didn't scale. So what people do now is a sender-driven protocol. Every processor looks at its part of the tree that it needs, that it owns, and that it has built locally, and decides which of my neighbors do I need to send it to. And then you make a copy of it and you send it to that neighbor. And so this is sort of some extra overhead to make the multiple copies, but then everybody gets the minimum amount of stuff that they actually need, and it scales well. So now I need to explain, how does each processor decide which of its neighbors needs to be sent which subset of the data? And so let me describe it for Barnes Hut, and then for fast multipole it's analogous. I won't go into the details. So I have 2 processors, call them J and K, and processor J owns a node. And the question it has to ask is, do I need to send a copy of this node over to processor K? Because, he'll need it. Okay, so how do I make that decision? How does processor J make that decision? Well, it owns the node, so it knows how big it is. It also knows what processor K owns, so it can measure the shortest distance from its node to any point owned by K. Because remember, I have built this data structure here. So if this node is the node that processor J owns, and it wants to know, and this is processor K, the green one, it knows how far apart they are. Let me go back here. So how do I decide whether to do it? Well, if this node is small enough that I can compute the force accurately just with its mass and center of mass, but its parent is not good enough, then I better send it. So this says, this is good enough for processor K to use, but its parent is not good enough. So I will send it. the other criterion for sending it is that it's an ancestor of that one. I need to go, I need to go through this node in order to traverse it in order to get to that one that I actually need. So in other words, I'm going to give the whole trail from the root down to the node that is small enough to be able to use this approximation. And then, if either of these are satisfied, then J will send a copy of node N to processor K. Okay, so that's the criterion. And for the fast multipole method, it's much simpler. It was just the interaction set. So that was those pictures here. So let me go back to this. So here is exactly what you need to send. If this is the interaction set, then you need to, and you're the interaction set of N, you need to send yourself to N. And that's what N needs. So that's simple tree traversal. Well, not simple, but it works. Okay. Okay, so let's go on to some performance results. So I'm going to work my way up through history, starting with the first Gordon Bell Prize to the most recent one. So this was, and so what I want to do is put down some of the performance data and then sort of walk through it and ask how well did they do. So this is going to be sort of a mental experiment that would be good for you guys to practice on your own one to say, am I scaling well? So this was 512 processors, 8.8 million particles uniformly distributed. They were using Barnes Hut, and they were asking for just 2 to 3 digits. And the total run time turned out to be 114 seconds. So how did that time break down? Well, the first step, where they gathered all the, where they sent a random subset of the data to one processor to build the octree, this is 3D octree, that took 7 seconds to sort of, estimate what the octree should look like. Then broadcasting that octree to everybody and having everybody send their particles to the final destination, that took another 7 seconds. Then, doing the tree traversal, going from the children up to the root to compute all the masses and center of masses, that was, so there's some real floating point work there. That took 33 seconds. Now, how much of that time going from the children, the leaves all the way up to the root was communication? It was 6 seconds. So most of it, fortunately, 27, 33 minus 6, was spent doing useful work. Then, what about the force evaluation? So that means for each particle, I need to traverse the entire tree. That's the lion's share of the work. That took 54 seconds. And finally, how well load balanced was it? What's the difference in runtime between the slowest processor and the fastest one when it was all done? 7 seconds. Okay, so the question is, how close are we to sort of perfect? And one very coarse way to say that is to say, well, let's suppose that the best I could do was force evaluation. Let's suppose that all of this other overhead, decomposing the domain, building the octree was free. Suppose that was infinitely fast. So I'm only care about the force evaluation. And let's suppose that it was perfectly load balanced, that I didn't have this there. How long would it have taken to do it in this very, very optimistic case? It would have taken 54 minus 7, or 47 seconds. So let's compare 47 versus 114. That's not so bad. It's a factor of 2.5 off of absolute upper bound in how much faster you could go. So that's one way you could evaluate it, and you could do the same sort of mental exercise for your final projects, whatever's appropriate for them. Now, what happens when they did the non-uniform analysis? It went from 114 seconds to 160. So in this case, it became more expensive as things became non-uniform. Okay, so this was 1992. Let's fast forward to 1999. We'll get to present day shortly. So this was in David Blackston's PhD thesis, and he tried to crank the error down to 4 decimal digits. And he ran on up to 32 processors of a Cray T3E, and this was the fast multiple method. And he was up to 80% efficient. But let us look just to understand the scaling at a uniform case and a non-uniform case, just going from 1 to 4 processors, and ask ourselves how it scaled. So in the case of 50,000 particles, uniformly distributed, on how big was the tree, it turned out it was 2,745 nodes. And it built the same tree whether or not it was 1 processor, 4 processors. And since it was uniform, the tree was not very deep. It was only 4 levels deep. What happened to the timing? as it went from 1 to 4 processors, it sped up from 172 seconds to 39 seconds. It was a speed up of 4.4, which is bigger than the number of processors. So first sanity check, does that make sense? And the answer is yes, because when you quadruple the number of processors, you get 4 times the hardware, which includes 4 times the cache, right? So it's having, spending more time doing, local cache hits instead of, accessing slower memory. So it's reasonable to expect a slightly bigger speed up. But the big speed up versus the direct and squared algorithm is a factor of 50. So that's the best news. Now here, maybe a little more surprisingly, so let's do the non-uniform case. And in this case, all the particles were originally distributed on the surface of an ellipsoid, just kind of artificial, but that's definitely not uniform. In that case, the tree had a lot more nodes in it because it had to sort of go much deeper in the tree, down to 10 levels in order to finally build it. But it also went a lot faster. So the fast multipole method was able to take advantage of the fact that there were these dense clusters, and it was 15 seconds going down to 2.4, a speed up of 6, and 500 times faster than the direct algorithm would have gone. So this was, a nice result there. Okay, so that's 1999. Let's go up to 2010. And so this was the first time people did a very, very careful analysis of all the architectural options that were available to make this run faster. And one of the co-authors I should mention is Richard Vudock, who's a faculty member at Georgia Tech and also a former student from here, and also a former CS267 GSI, just so you know. And so this was interesting work, not only because of the exploration they did comparing GPUs and multi-core machines, but they also used the kernel-independent fast multipole method that I mentioned before. So this is the one that works for arbitrary potentials, not just inverse square laws. So they tried this on 3 different platforms and a GPU, 3 different multi-core platforms and a GPU. So the Intel Nehalem, AMD Barcelona, and a Sun Victoria Falls. And so what were the speed ups that they got? So in the case of Intel Nehalem, this was a 2-socket platform. There were 4 cores per socket, and you could run up to 2 threads per core, which means there was 16-way parallelism possible. They got a speed up of 25. Where did that come from? I'll do the breakdown later. That's because there were a bunch of sequential implementations, sort of algorithmic optimizations they did that I'll describe, plus the parallelism from this. In the case of the Barcelona, 2 sockets, 4 cores per socket, just 1 thread per core, so a potential of 8-fold speed up just from parallelism, and they got a 9.4, again, from doing all these other optimizations that I'll tell you about. The Sun Victoria Falls is an interesting platform, 2 sockets, 8 cores per socket, and it can run up to 8 threads per core, but they're not really running in parallel. It's something called hyperthreading. And so that means that only 1 thread is running at a time, but if that thread stalls because it's done a memory read or something, then on the next cycle, the next thread can start. So it can always keep things busy by sort of hiding the latency. So there's a potential of 128 threads, and there they got a speed up of 37.6. So there will also be some GPU analysis. It turns out that GPUs were not very good at all the irregular stuff that was done here. It was only doing sort of the final part, which was evaluating forces, which were which is a better match to the GPU architecture. And so the overall speed up was not that great of a GPU over the multi-core platform. So we'll see how that worked. So as I mentioned, this is using something called the kernel-independent fast multipole method. It applies to any kernel that looks simpler the farther away you get, not just gravity. And all you need is a subroutine, which takes 2 inputs and returns the potential between those 2 particles. And so, for example, there's modifications on Laplace, Stokes theorem, Stokes potentials, all those things. So how does it do it? So suppose you have a box with a bunch of particles in it. How is it going to compute an approximation to it? What it's going to do is replace that box by a circle that surrounds the box. And on that circle, it's going to put a bunch of evenly spaced points. And then it's going to assign masses, call them masses, to each point on that circle and pick them to approximate whatever's going on inside the box. So you could have as many points inside the box as you want, but it still might just pick a circle with 10 points evenly spaced around the circle. And then it will do some interpolation in math in order to figure out what should the masses be at all of those points on the circle in order to approximate everything inside. And since it is spending a lot of time evaluating functions at uniformly spaced points in a circle, you can imagine that there's an FFT involved. So tuning the FFT is also part of the game that they played. And they were using FFTW and so forth. So here's some of the other things that they tuned. They did a bunch of low-level SIMD vectorization. That's a natural thing to do on this architecture. But they also used a new instruction that was available, and that's called an approximate reciprocal square root. So it takes a number x, and it computes 1 over the square root of x to 12 bits of accuracy. And so why would that come up? Well, if you're doing something that involves, something that decays farther away, it's no surprise you need 1 over the square root of x as part of your approximation. And it turns out that 12 bits, that's not enough. It turns out if you do one step of Newton's method, which costs you another 3 multiplies and 1 add, you can double the number of bits. Newton is quadratic convergence, so you go from 12 to about 24. It's not correctly rounded, but who cares? It's good enough for the purposes of this, and they got really significant speed-ups by using this particular interesting instruction that was available. They played with the data structures a lot. You can have structures of arrays, arrays of structs. They all have different memory access patterns. So it turns out that converting from one expansion, which I talked about before, like converting an outer to an inner expansion, what are you doing? What's the actual core? You're taking linear combinations of the coefficients of one polynomial to get the coefficients of another polynomial. It's a matrix vector multiply. That's all it is. So this algorithm really spends all its time doing lots of local matrix vector multiplies. And so the question is, do you pre-compute the matrices and just call GemV, or do you compute the entries of the matrices on the fly, because they're given by formulas, and then do the matrix vector multiply? And so if you compute the entries of the matrices on the fly, rather than pre-computing them, that's called matrix free. And it turns out that gave them speed-ups, rather than pre-computing all the entries. And then they used FFTW for that. They used OpenMP for the parallelization, and they also had to decide, how deep does the tree go? How many particles should I leave in the bottom? That was called Q, and just do a direct Q squared algorithm at the leaves of the tree. So Q was another tuning parameter. So let me show you some of the results. And so this is just single core optimizations. Let me get this right. So no parallelization here at all. And so this is just how much speed up you can get on a single core, double precision, and ellipsoidal. And here and 0% is that means that's the unoptimized algorithm, the naive algorithm. So 0% means you're running at the naive algorithm. 100% means you're running twice as fast. 200% means you're running 3 times as fast, 4 times as fast. So up is good. And these are all the different phases of the algorithm. So there's building the tree. There's going from the leaves to the root, that's going up. And then there's all these other tree traversals, which I won't go into the details of, and these are just names of different data structures in the algorithm. And then finally there's going from the top of the tree down to the bottom to actually evaluate the forces. And so and all of these bars are color-coded by which optimization gave them that much of a boost in the speed. So you can see that using the SIMD instructions, got them up to, some decent fraction of going twice as fast. Then replacing the 1 over the square root of x function by this approximation, and then doing one step of Newton's method, that gave them a really big boost. That's the yellow speed up, rather than using the built-in hardware square root and division functions. Then using structure of arrays instead of array of structs gave them the green bars. And then replacing the matrix vector multiplies by just recomputing the matrix every time you need it gave them this other boost of the blue. And so that gave up to a 5 times speed up on some things. And this was the only place where they needed to do the FFT, and that benefit was from running FFTW. Okay, so this gives you some sense of what all the speed ups are. There's more data. This is just single core. So the next tuning parameter is how many points do I leave in each box at the leaves of the tree, right? So I'm going to just do this q squared interaction at the bottom. And so here is the performance. Well, here's the time. So down is good, time in seconds, versus q on the horizontal axis for 3 different versions of the code, the unoptimized serial code in blue, the optimized serial code, and the optimized parallel code, which is the fastest by far. So it turns out that 100, using q equals 100, which, so there was 100 by 100, direct interaction was the best thing to do in the unoptimized code, and it ran in 168 seconds, and it went all the way up to 250 or 500 for the optimized parallel code, and it ran in 10.4 seconds. So that was the right thing to do there. So there was, just doing the direct n squared interaction is very much more efficient, and so it just does flops at a very high rate. So it was good to go down to 250 or 500 direct interactions. So finally, let's put it all together. And so here are the parallel speedups, and this is for a whole bunch of different platforms: Intel Nehalem, AMD Barcelona, Sun Victoria Falls, 1 GPU and 2 GPUs, and for a uniform distribution of particles, and for particles non-uniformly distributed on an ellipse. And the vertical axis is the time on a log scale. And it's all normalized to 1 Nehalem processor, sequential, no optimizations, naive code, that runs in time 1. So everything is relative to that unoptimized, naive Nehalem code. And so you can see that if I take the naive Nehalem code and just optimize it doing sequentially, so this is sequential code, it goes like 7 times faster. If I then parallelize it with OpenMP, I get up to there, that's the yellow. And then if I say, let me ignore everything except the time, building the tree, all of that stuff, and I'm just going to say how much faster does evaluating the force go, it's a factor of 55 times faster. So why do I distinguish this and this? If you only wanted to compute the forces once, this would be your speed up. But if you want to compute the forces many, many times from many different other particles, then the top of the green line is better. So there are different use cases. So Barcelona starts about as fast as Intel, but then it ends only at 30 times faster. Victoria Falls starts 10 times slower, but it speeds up by a factor of 30, but still its 128 threads only brings you up to a factor of 3 times faster than a sequential Intel processor. And for the GPUs, since they can't do any of the irregular work that involves building the tree and all of that, we're only counting the time to evaluate the force. And 1 GPU gets you a speed up of 32, 2 GPUs a factor of 60, so it's about linear, but it's not much better than just using a Nehalem. And the story is about the same for the elliptical distribution. Okay, so let me summarize, last slide. So how close am I to hitting the lower bound in communication for all of these? Because a lot of the optimizations were to minimize moving data around. And let me distinguish the hierarchical methods, which is what this whole lecture was about, from the direct methods. So most of my time today was spent reducing the arithmetic from order n squared to order n log n. And that was great for minimizing the communication too. We worked hard by building these locally essential trees, so everybody got, we replicated the data so that you didn't have to communicate when you actually evaluated the forces. But it's an open question as to what a lower bound would be, because we're only computing an approximate answer, and so how do you, and the approximation accuracy is going to depend on the particle distribution, so we don't really have an approach to say we're close to a lower bound. I mean, I did this sort of back of the envelope analysis saying how close are we to some sort of peak speed, and it's pretty good, but that's an open question. But there is an example where we have an actual theorem and an algorithm for hitting a lower bound. And this sort of refers back to something I did before. Let me just tell you the theorem. So this is, suppose we're just running the direct order n squared algorithm on P processors. And what I want to do is ask how much data do I have to move around between all the processors in order to implement that. And this is still interesting because remember, we're running this algorithm at the leaves of the tree, of the hierarchical tree. So suppose I have P processors, and I'm doing all n squared interactions, and each processor has a memory of size capital M. What's a lower bound on how much data I can move? It turns out that the answer is that each processor must communicate at least, so it's lower bounded by, the number of flops that it's assigned divided by m. So let's just remember what matrix multiply was by comparison. Matrix multiply was the number of flops, that was n cubed divided by p, divided by m to the 1/2. So this is even better than matrix multiply. It scales much, much better because I have a bigger power of m in the denominator. And the number of messages that I have to send is, again, the number of flops, now divided by the square of the size of the local memory. Now, this is true not just for the direct n squared algorithm, but even if I have a cutoff. This is the lower bound. And in that case, I replace n squared over p by just however many interactions you have. It's still the same lower bound. Okay, so the question is, when is this attainable, right? Because m could be, it has to be at least big enough to store one copy of all the particles. But what if I make it bigger and bigger? So it turns out it's attainable when m is the minimum size, so each processor has n over p particles. I have to have at least that much memory. But it's still attainable when I go up to n divided by the square root of p. So I can have up to the square root of p copies of the number of particles. And so let's just look at these two cases. If I have the minimum amount of memory, and I plug it in, the number of words moved is n. And that's easy to see how to attain. I have backup slides on that. And the number of messages is p. So what if I go to the other extreme? If I have square root of p processors, the number of words goes down by a factor of the square root of p. So that's a big drop in how many words moved. And the number of messages goes down by a factor of p. And we've implemented this, and we've gotten 12x speedups on the direct n-body algorithm. And so this is, a worthy thing to do. And it might even be useful, as the base case for the hierarchical methods. So I think I will stop there and ask for any questions. And the algorithm that actually attains this is on the hidden slides. So any questions about class projects? Okay, well, it was fun reading all your project proposals, or at least I read 1/3 of your project proposals, since there are 3 instructors, and so please feel free to ask more questions. Okay.